Hi, and welcome to H2.6 Angular Momentum. In this lesson, students will be able to analyze the angular momentum of a rotating rigid object. So, critical thinking. How does a figure skater control their angular velocity as they spin? They have the ability to speed up their angular velocity and slow it down. They could spin faster or slower. How do they do that? Pause the video, think about it, and then think about it some more. So, use what we know now to describe what you think. So here's a GIF of a figure skater spinning faster. So slow, and then as she pulls her arms in, she's spinning faster. How does how does her body know, okay, I'm putting my arms closer to me, that means I spin faster? How does that happen? Well, we have to think about moment of inertia. So the idea is the more mass you have on the outside, the further the mass is oriented from the axis of rotation, the greater your moment of inertia. If there's more mass towards the center, more mass closer to the axis, you're going to get less of a moment of inertia. So now let's go back to thinking about linear variables. We're talking about more mass and less mass. And how does that affect your velocity if you have more mass and less mass? So here in these situations, her mass is further away from the axis of rotation. So that means that if the mass is further away, you're going to have a greater moment of inertia. As she pulls in her mass as close as she can to the axis of rotation, then all of the mass is closer to the axis and you have a smaller moment of inertia. So again, let's think about when we were talking about mass and velocity, right? What's mass times velocity? Momentum. So let's think about linear momentum first before we explain this with angular momentum. We said that momentum is conserved. So same with this situation here. The total momentum is conserved. She has some rotational mass and some angular velocity that she's going to have some angular momentum. That angular momentum is conserved. What she can do is change how her mass is oriented, thereby changing her moment of inertia. And if we look at our linear variables, what happens if we can now change the mass? Before, we were always saying, okay, you either speed up or slow down in your car. You could change your velocity. Now with the rotational variables, we could actually change the moment of inertia. We can change effectively what the mass is. If the mass, what's happening? She's going to a smaller moment of inertia. If the mass decreases, what has to happen to your velocity in order to maintain the conservation of momentum? Your velocity must increase in order to compensate. That way this term is equal to that term. The initial momentum is equal to the final momentum. So it says if mass decreases, what must happen to the velocity in order to maintain the conservation of momentum? The velocity must increase. Very good. So angular momentum, we use a capital L to represent angular momentum. The angular momentum of a body rotating about a fixed axis is the product of the body's moment of inertia and its angular velocity with respect to that axis. It is directed in the same direction as the angular velocity. So it is a vector quantity. What do you think the units might be? Okay, so we know about momentum, it's the mass times velocity. This is the moment of inertia times the angular velocity. Pause the video, think about what the units might be. We're going to have the moment of inertia, kilogram meters squared per second. Why not kilogram meters cubed per second? Because remember, it's angular velocity in radians per second, not meters per second. Tricky, tricky, tricky. So speaking of, make sure that the angular velocity is in radians when you're using this formula. So the angular momentum L is equal to I omega. Where is this formula in your reference table? It's going to be right here, the last formula in this unit. And it's actually the very last formula in the mechanics unit as a whole. All right, so after this, we're doing electrostatics, which is not in the mechanics unit. So this is a big day. Let's do an example. It says a bowling ball of mass 5 kilograms is rolling down the alley at a speed of 9 meters per second. The diameter of the bowling ball is 22 centimeters. Calculate the moment of inertia of the ball, calculate the angular velocity of the ball, and then once you have those two, calculate the angular momentum of the ball. Pause the video if you want and try this out. Let's start by writing our givens down. The mass is 5 kilograms. They tell you your linear velocity is 9 meters per second. And then their mean, they tell you the diameter. And their mean, they tell you it's in centimeters. So that means our radius is half that much. And we're going to go into meters for our radius. Part A, find the moment of inertia. Part B, find the angular velocity. That will help us with part C. Find the angular momentum. So for this one, it's a bowling ball. A bowling ball is a solid sphere and it rotates through its center. So that's 2/5 mr squared. So for part A, we have our moment of inertia for the ball is 2/5 mr squared. You plug in and you get 0.0242 or 2.42 times 10 to the negative 2. What are the units for moment of inertia? Kilogram meters squared. Okay, nice. Part B says to find the angular velocity. Well, we know what the linear velocity is. Don't forget about the switcheroonie there, okay? In your reference table, there's a formula that looks like this, okay? And it'll pop out an answer in radians per second when you use this. So if you wanted to rearrange, you take your linear velocity divided by the radius. That'll give you your angular velocity. We did this in the previous lesson. Hopefully you didn't get tripped up. It's like, where the heck did this term come from, V over R? That's in your reference table. So the angular velocity is 81.8 radians every second, radians per second. Part C, our good old friend, the momentum equation, but instead of P equals mv, it's L is equal to I omega. This is like mass times velocity, okay? Remember? So the angular velocity, and I'm going to write it with the units so you could see 2.42 times 10 to the negative 2 kilogram meters squared. And then the angular velocity is 81.8 radians per second. So we think of radians as like unitless when we do our dimensional analysis. So this is a kilogram meters squared per second, like that. So when you do the multiplication, you get an angular velocity, an angular momentum of 1.98. And then what are those units for angular momentum? Not a kilogram meter per second, but a kilogram meter squared. That's your like rotational mass, your moment of inertia per second, a radian times a radian per second. That's your angular velocity. So just a kilogram meter squared per second, that's your angular momentum unit. So we can definitely have some fun with conservation of angular momentum. It says the total angular momentum of a system remains constant or is conserved if the average external torque acting on the system is 0. So we started off the video by talking about this concept with the ice skater. Let's continue the idea of conservation of momentum by doing something similar to the inelastic collision problems that we did in Unit 9. It says two disks are rotating about the same axis. Disk A has a moment of inertia of 3.4 kilogram meters squared and an angular velocity of positive 7.2 radians per second. Disk B is rotating with an angular velocity of negative 9.8 radians per second. Radians per second. The two disks are then linked together without the aid of any external torques, so that they rotate as a single unit with an angular velocity of negative 2.4 radians per second. The axis of rotation for this unit is the same as that for the separate disks. What is the moment of inertia of disk B? So the situation is you have the same axis, and then disk A combines with disk B, and now they move with a different angular velocity. Hopefully this situation seems similar. Like I said, it's similar to the inelastic collisions problem where we had two separate objects and then they combine together and stick together and move with the same velocity. So if you want, you could actually pause the video and try this on your own. You have enough information now to try this one. Let's start by writing our given information. So the moment of inertia for disk A is 3.4 kilogram meters squared. And they tell you the angular velocity initially is positive 7.2 radians per second. So hopefully these are bringing back, oh yeah, the subscripts, AI, and then, oh yeah, the direction of the velocity really mattered when we were doing those collision problems. So this is just another collision problem. We're looking for the moment of inertia or of disk B. This would have been like we were looking for the mass of one of the objects before. We know the initial angular momentum of disk B is negative 9.8 radians per second. So it looks like disk A is rotating this way, disk B is rotating the other way, and then they combine and they have an angular velocity, a final angular velocity together of negative 2.4. So disk B wins, and when they combine together, they end up moving in this direction. But it's going to be slower than before, right? Because this was some of that angular momentum was going in the opposite direction. Okay, so yeah, what is the moment of inertia of disk B? So we have our conservation of momentum. Initially, they're separate. So we could say the angular momentum of A plus the angular momentum of B is equal to the angular momentum of A plus B when they're together like this. Okay. And then remember, angular momentum is just the moment of inertia times your angular velocity for A and B. And then this is when they combine together. So the moments of inertia, you could think of it as rotational mass, combine together as one unit, and they move with the same angular velocity. Hopefully this looks familiar. For this situation, it's very similar to our inelastic collision problems that we did in Unit 9. So now we could just plug in 3.4 times positive 7.2 plus we're looking for IB times negative 9.8 is equal to, we know what this one is, 3.4. Again, we're looking for IB, and the final angular velocity is negative 2.4. So we have one equation with one unknown. We just need to do some algebra. So I just did this multiplication and I distributed the negative 2.4. Then I added 8.6 to both sides to get 32.64. And then you add 9.8 to negative 2.4 to give you the 7.4 times the moment of inertia for B. So then you divide, then you get the moment of inertia for B to be 4.41 kilogram meters squared. Nice. So we could use what we already learned for some new fun situations. This happened to be, they give you the moment of inertia, so keep an eye out. You might have to calculate it. And then, yeah, they gave you this, so that's nice too. Okay, so now it's time to come full circle and do a problem that's similar to the one that we did in the beginning of this video with the ice skater. So that wasn't actually like a collision problem like the previous example was. You could still think about the conservation of momentum when it's just one object, and maybe that object is changing their moment of inertia, which ends up changing their angular velocity, but their actual angular momentum stays the same. It is conserved. So instead of an ice skater, we have a satellite. The problem says an artificial satellite is placed into an elliptical orbit about the Earth. Telemetry data indicate that its point of closest approach, perigee, is 8.37 times 10 to the 6 meters from the center of the Earth, and its point of greatest distance, apogee, is 25.1 times 10 to the 6 meters. The speed of the satellite at perigee is 8,450 meters per second, so that's faster than what it is at apogee. Find its speed at apogee. If you'd like, you could pause the video and try this one out. Just remember, we're talking about the conservation of angular momentum. They're giving you enough information here to find something. I'll give you a little hint. I see a radius to an axis, but that radius is changing. So what's actually changing there? And then this is a velocity. They're giving you the tangential velocity. So make sure you keep that in mind. But again, you have the velocity and the radius, so you should be able to work with that. If you need one more hint, you can approximate the satellite as a particle because its size is so small compared to the vast distances that we're talking about here. So you can approximate it as a particle. Pause the video, try it out. So let's start this by writing the given information. We have two different radiuses here. So at perigee, it's 8.37 times 10 to the 6 meters. And at apogee, it's 25.1 times 10 to the 6 meters. They don't tell you the mass. They do tell you the velocity at perigee is 8,450. And we're looking for the velocity at apogee. Okay, so the strategy here is going to be to use the conservation of momentum, but instead of like initial and then a collision and then final, we could think of it, I mean, you could think initial and final, but let's use the subscripts A and P for apogee and perigee. Okay, then we know the angular momentum is equal to your mass times your velocity, but it's your moment of inertia times your angular velocity, and that's going to change depending on your position in the orbit. Why does it change? Because your moment of inertia is changing. We're going to approximate this as a particle. So for if we wanted to like write out the equation here separately, maybe that makes it easier to see. So that's something we also know is the moment of inertia of the satellite at these different positions. At least we know the equation for it, and we're going to plug that equation into this equation. So all we did was plug in for I. We know that's equal to mr squared, and the radius is changing. All right, the radius is changing. Okay. So at this point, actually, we can see that if you divide both sides by the mass, which you can do, if you were confused by how that worked last time, whatever you do to one side, if you do it to the other side of the equation, all the terms, then the equation holds true. They're still equal to each other. So we can divide this out, is the point. And then we're left with something nicer. So far we have RA squared omega A and RP squared omega P. I mean, you could have waited to cancel out until later, but when I see that, I want to cancel it out. I want to get rid of it. All right, so they tell you the velocity, and in our equation we have the angular velocity. So that tells me I'm going to need to use a switcheroonie. We know from the reference table that the tangential velocity is equal to r omega, which means that omega is equal to the tangential velocity divided by the radius. So we're going to plug this in over here. So for apogee, we have r squared times the velocity at apogee divided by the radius. This is your angular velocity at the apogee. You're changing your rate of rotation just like the ice skater is, right? So you sped up and slowed down. So this is this, okay? This is V over R, switcheroony. And now we could cancel out some other stuff. So r squared divided by a radius, r squared divided by r, you could cancel out one of those r's. And then what are you left with? RA times VA, oh man, my r's are starting to look like v's, is equal to RP times VP. And look at here, one equation, one unknown. Now we're happy, but we're not happy because I kind of ran out of room here. So at this point, the strategy is to solve for VA by dividing by RA. So VA is equal to RP VP divided by RA. Carefully plug in your numbers, making sure that RA is on the bottom, and you get 2,820 meters per second. I rounded, I used significant figures. Really, when you plug it in your calculator, you get 2,817.79, but we'll round it to 2,820. So as we expected, we were going faster. This was 8,450, and then the further you go out, the slower your tangential velocity and your angular velocity, as per Kepler's law. What is it? The third law of motion, I believe. No. Yes. No. The second law of motion. All right. Yep. Nice. All right. That's about it. Thanks for watching and have a great day.